voice channels, bring them to these programmable processors, change them to packets, the IP packets, and then put them on the other interfaces. So we could able to do this amazing work all by Pakistani engineers like you in 8 months. So we, from the drawing board to actual, this chip was just 8 months. So 8 months we designed it, we put it on a board, we put it in our system. That was a very interesting work we did. And that really helped me, this work helped me to put this book together, which got published by John Wiley last year. And we have several patents in this technology as well. Like we have a patent on the top level, as I mentioned, that was more challenging. How putting multiprocessor on a chip. So that's a very interesting, you can just search for this patent with my name, and Mohsin was another inventor. So that's the work which we did. This is the chip. Not exactly it was like this, but it was almost like this, that there were processors, there's an array, the rows of processors which we designed, and we call these are application specific processor. This processor would only do DTMF detection. If you know DTMF, it is like the very first thing in telephony you need to do is you need to detect the number somebody is dialing. So 2,000 people dialing numbers you need to detect, and sometimes people within the call they are just dialing, or they are just pressing keys, especially if you are doing a credit card transaction. So in the call you say, please enter your credit card number now. So it's something within the call you have, needs to be always alive, because as a processor you don't know what is happening on your speech call. So if you detect a DTMF tone, you need to detect the whole thing. So for all the calls you need all the time, every buffer has to be searched for DTMF detection. And then another challenge in that is echo cancellation, because voice over IP, the biggest challenge in voice over IP is that you need to remove the echoes, which are caused because of the hybrid which you have in the network. I'll not get into the details, maybe in the networking course. And then the actual compression, the compression and decompression. And because the data is moving across these layers, then designing the network, the top level, that how you basically take data from one processor and make parallel transactions. Things are moving through the chip. Very, very interesting design we did. And then because a chip would cost you a lot of money to spin. Like a chip, just to get one spin of the chip will almost cost you $1 million. This complexity. Like a bug, if you leave a bug in your code, it will cost a company $1 million. It's that simple an equation. Very, very expensive because of the details that are involved in actually getting something manufactured. And so we got it manufactured from Lightspeed Technologies. We call this Avaz. So it says Avaz. So its name, the name of the chip was Avaz because it was processing voice. So then, for some reason, we focus more towards doing things in Pakistan, and this brought us to use FPGAs. And this is way back in perhaps in initial, in like at least 8-9 years back, this was the statement which I would put in my course outline, that I consider FPGA as the most exciting invention of electronics after transistor. It is an amazing device that can take any configuration as per the designer's desires. The technology of special interest to engineers in developing countries, as it enables them to design and implement multi-million gates logic. They can realize astonishing solution to mathematically intractable problem. Once we were doing chip, the ASIC, we knew that you require a huge amount of funding to do amazing work in technology, because if you have money, you may be very creative, but unless you have that money, you cannot get it fast. But then once we started working in Pakistan, obviously nobody would give you $1 million to to develop a piece of technology which is that little in size. So then we found that FPGAs are amazing to actually implement your design. And there's several work, and we have been now taking this to competition, winning awards, and it's a whole platoon of awards I have in my office, and I don't know what to do with these, but we have been just once we are taking these and showing to people, they really get amazed to see what the things we are doing in Pakistan, alhamdulillah. And I'll be just sharing some of our work with you. So the FPGA is critical, and that's how the focus would be FPGA, not ASIC design, because the same reason that in Pakistan it's difficult for you to get into ASIC business. So that's how we started developing our IPs for ASIC, and then we shifted towards FPGAs. FPGAs is a reconfigurable logic. It's a block, this black box, which can take any shape. And again, we'll spend more time. It's just an introduction, so I'm just giving you a little bit of everything. You know. So the FPGAs are reconfigurable devices. They are, you can just buy them off the shelf. They can cost from $50 to maybe $5,000, $10,000, $20,000. Depends on how complex a device you want to buy for your system. So it's usually the crudest, the simplest FPGA will look like this. It has a logic block and an interconnection switch. This logic block, depending upon the number of inputs it takes, it can take any shape, and that's the beauty of it. And that shape can be configured by a bit stream which you load, and that configures it. For example, a very typical simplest block with 2 input and 1 output logic means it can take shape of any 2 input logic you can think of. Any 2 input, 1 output, right? So any 2 input, 1 output logic can be programmed by setting the bits, these 4 bits of this particular reconfigurable logic block, right? As it says, either it's a 0, 1, 0, 1, 0, 1, 0, 1. Now the task of the tool, which we say a synthesis tool, is to take your higher level of abstraction Verilog code, and if the FPG has nothing but just these 2 to 1 input tables or the blocks, it'll break it down into statements or logic which has only 2 input and 1 output. For example, you want to implement an 8-bit adder. 8-bit has 4 2 bits, so it'll consume 4 2 bits of these black boxes. You know, if a black box has only one of these, it'll consume that. I'll say I have consumed that. And you say, no, I don't want an adder, I want to implement a multiplier. So it'll just requisite number of, black box will say, okay, now I'll take the shape of a multiplier. So you can basically make it look like anything unless it is confined, like it can fit into that area, which is the area of the FPGA. So for example here, this is the logic, x bar, y bar, x1 complement, x2 complement plus x1, x2. This is the logic, for example. And this is the truth table of the logic. I'll find out the way it is designed is such that this truth table 1001 gets set here, 1001. So these are the bit stream which you load, gets into these locations and make this particular logic block to implement this logic. And you can check it. It says if both inputs are 0, 0, output should be 1. So it says if here you have a 0, here you have a 0, output should be 1. If here you have a 0, here you have a 0, 0 mean upper value of the mux. Okay, so it is 0 gets here, 1 gets here. And again a 0 means this one will go and get at the output. Right? So this, it is guaranteed that this particular bit stream will implement this functionality on FPGA. So now there are FPGAs which usually 6 input lookup tables, for example. So there are 6 bits at the input, 1 bit at the output. Let's say your logic requires 6 input and 4 output, for example. So you have a logic which requires 6 bits as input and 4 bit as output, and you have these lookup tables. So this is a lookup table which says you can have 6 to 2 lookup table. Okay, if it perfectly maps, your logic perfectly maps into this lookup table, if your logic has 6 inputs and 2 outputs, obviously you cannot constrain your logic, it depends upon the code and whatever you are doing. Let's say it is 6 input and 4 output. So what the synthesis tool will do, it will consume 2 of these. It will feed in the same inputs here. Okay. The same inputs to look 2 of these LUTs, and it will give you 6 input to 4 output lookup table. If you say no, I have 6 input, okay. So coming back. So the magic in the FPGA is that these black boxes have this characteristic or the character that it can take any shape, and you can reprogram it millions of times, as many times as you want. So if there's a bug which you left in your code, you can come back, change the code, resynthesize it, and just download it. And nowadays they are coming with the runtime reconfigurable FPGA. Like part of it you can change while you are running rest of it. So it's not that only one time, that you can continuously keep changing the logic. Means it's like software, it's like the programs which you run, and it's all the time your hardware is changing underneath. It's almost like this, maybe fictional, but it's almost like you have a Pentium, then you have a Sun machine, then you have an ARM processor, then not exactly, but this is what it means, that you can actually change the hardware underneath as runtime. But the tools are not supporting the features they have added in FPGAs, because very difficult for you to think in terms of hardware changing all the time. For every instruction, your instruction set is changing, your underneath hardware is continuously changing every cycle. So it's very difficult to perceive and design, but you can find people doing research, writing papers, writing theses in runtime reconfigurable FPGAs. But and then this is the interconnection. Like if your logic will not fit into this, it fits into 4 of these, they automatically get interconnected. The interconnections are also programmable. So so this is basically the idea. The whole idea of FPGA is there is something which is reconfigurable. Right? It can just take any shape. And then because they have to compete with the this is a 3-input lookup table, and there are thousands of these lookup tables in an FPGA. Right? So this lookup table primarily again can implement any 3-bit to 1-bit functionality. Okay. Then because now there is this competition where who are competing. Obviously on one part of the spectrum is programmable processor like Pentium. Still, like we are developing products, still people compete with us. They'll bring blades of machines having multi-core Intel processors. This is one part of the competition which you have to just you go. And then there are products which are coming. They will never try to do things in hardware, because doing things in hardware is difficult. Programmers, they like to just write C code, and then they use a powerful engine, maybe multi-core machine, to implement it without they worrying about the parallelism and the functionality and exploiting all these things. So on one spectrum of this competition is multi-core Pentium machines, blades, servers, all that is still there in the competition. And then there are specific application-specific processors like digital signal processors. Okay, and there are general-purpose processors like ARM. So MIPS and Motorola microprocessors. So there's several programmable devices, digital signal processors, Pentium processors, and then to compete with them. This is the FPGA market. FPGAs are not easy to design. Not every engineer can just program FPGA, and you will realize it in this course. Very difficult to design, very difficult to map applications, but gives you a lot of power in your hand. So because the FPGAs are now competing with all these entities in the market and for the high-end products, so they started putting, let's say DSP, they had only one multiplier. They used to have only one multiplier. Most of the DSPs, if you look the DSPs, old DSPs from, let's say, analog devices, ADSP 2100, only one multiplier. PMS 320 C55X, only one multiplier. C54X, only one multiplier. So they were just one multiplier, but knowing that the applications require more and more power, so the DSPs have a very different approach to tackle that. They started putting more multipliers in their architecture. They said, let's put 2 multipliers, let's put 4 multipliers. This is the approach taken by the digital signal processors architects. Put more, but if you have 4 multipliers, the programmer has to use it, or the compiler needs to exploit the parallelism in the instruction to use 4 multipliers, which is very difficult. In a single instruction, if I ask you, there are actually, these are called VLIW instructions, that you have to use all the power in your programmable machine. At instruction level, it's difficult. There is another approach which is taken by the Pentium. They said put more multiple cores at another level of parallelism. Say let's find out the application, break it down into multiple threads, run few here, few here, few here. You know, so that's another approach. GPU is yet another approach, which is also has a graphical processing unit. They have like 64 cores, single instruction, every processor doing the same work. Also very competing in the same market space. But the FPGAs to take over, some of the market for the Pentium and the DSPs, they also started putting more of the multipliers, adders, and programmable processor in their devices because they wanted to take over the market from the digital signal processors. So now today you find very interesting architectures like, for example, this Xilinx FPGAs. They have this DSP48 block, which is a multiplier and 40 odd bit adder, and many of these, and one with a PowerPC in it, and the Ethernet interface, and this interface, and that interface. So this is how they are just taking over the market from the vendors and helping people like us to compete in that domain, but bringing totally a different solution in the market. And I'll be showing you those solutions. This is one of our solutions which has won several awards for us, and we just actually signed a customer in Saudi Arabia. And there we were competing with all these people who were coming up with the programmable solution. And Saudi Arabia means you are competing almost with everybody, like Germans, France, Americans equipment. So you're competing with everyone. Very high-end product, which is doing processing in 10 gigabit rate. This is what we were using. A single FPGA with 4 10G interfaces, bringing 40 gigabit of traffic inside our devices, and mostly doing things here, not putting a rack of server machines where you have all programmable processor doing the same thing. So that's the scale, the difference in the approach you take to compete with others. So this was our solution, putting this obviously in a computer on a PCI slot, and then putting it, all these physical interfaces, which is 10 gigabit fiber, then placing this box in the network instead of, having a complete rack in the network. And this is one of our products on the network side. And based on this platform, we have then developed several of these. Like we have bulk encryption systems, which can do bulk encryption at multi-gigabit rates. A series of products in this range which deals with the network traffic. So, but this is this is where you don't need any multiplier. Mostly, it's the internet packet that gets into your system, and you are parsing, you are comparing, you are doing this or that. It's a different product line, but it's very effective. It's a very effective way of designing things. This is yet another project which was funded by ICT R&D Fund, and there we said we will develop a system which can do massively parallel fingerprint recognition. So our target is, if there are, let's say, 100 million queries in a second, 100 million people are actually putting their fingerprint in this world to be verified, your system should be able to do it. So, and that's what we believe, that this is where the world is moving. Like Google searches, there are people who are doing Google searches everywhere. Just count the number of Google searches that happens every second. So we say, okay, now because the cloud computing will require people to authenticate themselves that they are the valid users. So they'll be putting their fingerprints, not today, maybe in 4 years, 5 years, 2 years time. So this is where the world is moving, that authentication will become very important, that you will have every device will come up with a sensor, and you have to swap your finger if you want to use or get your desktop any place you go, so that you get your desktop, but the people are comfortable and you are comfortable, that nobody else can actually sneak into your system. And that's what we believe, that this is an interesting product that, and again, massively parallel is honestly, it's very multiple layers of parallelism, like at what level you see the parallelism. We exploited the parallelism and to develop something, and I'll try to bring the board on which we are doing, for example, 6 million on a board.